Today we proceed with the study of linear regression, introducing two important topics, such as the use of qualitative or categorical predictors and the issue of interactions. So the important point is to note that some predictors are not quantitative, but they are qualitative. This means that they take a discrete set of values, and so they are called qualitative variables or predictors, but also categorical predictors or factor variables. To illustrate this point, we use an example, and in particular we refer to the credit card data, and in the next slide we show the quantitative variables. So we have 7 quantitative variables, and okay, let's see now the scatter plot matrix. These are the credit card data. These are the 7 quantitative variables. So you can see in each graph the scatter plot between 2 quantitative variables. And I'm not going into the details of the meaning of all the variables, but I will just note that an important one is the target variable, that the one that we want to predict, that is balance. Balance means the money that you have to give back to the bank, essentially. So this is the meaning of the balance, and these are the features of the individuals. And in particular, we have age, education, income, limit, and rating. You can see that some of the features are highly correlated. For instance, I can take a limit and rating. You can see that their scatter plot shows that their correlation coefficient is very close to 1. So you might consider using just one of the two because the other is not bringing any additional information. Other couples of variables like income with limit or income with rating are also quite highly correlated. And okay, you can look at the scatter plot matrix where you get a lot of useful information. In particular, it is also interesting to see what predictors are best correlated with the balance, because this tells you what are the input variables that are most likely to be useful in order to build your regression model. And you can see here from the scatter plot that limit and rating are actually well correlated with the balance. But let's go back to the qualitative variables. In addition to these 7 variables, there are also 4 qualitative variables, and in particular they are gender, male, female, student, and this means that the individual might be a student or not, status, married, divorced, not married, and ethnicity. And ethnicity is a categorical variable with 3 states: Caucasian, African American, or Asian. Okay, so let's see how we can deal with these qualitative variables. And in particular, we will investigate the differences in credit card balance between male and females, ignoring the other variables. So, in order to introduce this qualitative variable, we introduce a new ad hoc variable, a binary variable that we call xi, and the idea is that xi is equal to 1 if the ith person is a female, and xi is equal to 0 if ith person is male. The resulting model has this structure. So now we are considering just one predictor, that is the gender. Okay, so we have the intercept plus a linear term in the binary variable. And since actually this is a binary variable, we have 2 cases. If the person is female, then the model takes this form, so beta 0 plus beta 1 plus the error. And if the ith person is male, then the binary variable is equal to 0, so we have beta 0 plus epsilon I, the error. So by introducing this binary variable, we have split our model in 2. So we have a baseline model where we just have the intercept, and this intercept refers to male persons. And then we have a second model where the intercept now is beta 0 plus beta 1, and this is the intercept for female persons. So, okay, this is very simple way to deal with categorical variable. Let's look at the results at this point. So we have two parameters, beta 0 and beta 1. Beta 0 is the intercept. This is the coefficient which is estimated by least squares. This is the standard error. As we have seen, we have to compare the standard error to the absolute value of the parameter, and the absolute value should be at least twice, okay, for be safe, so to be sure that we can reject the null assumption that the parameter is equal to 0. Here it is much larger than twice, and this is something you can see also from the t-statistic and also from the p-value. So the p-value refers to the t-statistic, and it gives you the probability of getting a t-statistic equal or larger than this, and so you can see that it is very difficult by pure chance that if the parameter is 0, the t-statistic will be larger than 15. So you are quite sure that this parameter is different from 0. And what about gender? Now we see that the coefficient is 19 and the standard error is even greater than the coefficient. So the rule of thumb that the coefficient, the absolute value of the coefficient should be at least twice is violated here, okay? And you can see this also from the t-statistic. So the t-statistic is 0.4, which is not good. And as a matter of fact, when the parameter is equal to 0, it happens about 67% of the cases that you get such a large value of the t-statistic. So it's quite common to get this t-statistic even if your model parameter is equal to 0. So we do not trust this beta 1 parameter, and it could be well equal to 0. So we are just estimating noise. Okay, but of course it may happen that we don't have just two levels. So in the case male-female we had just two levels, but it will be that we have more than two levels, and this was the case of ethnicity, because in the case of ethnicity we had three levels. In particular we had Caucasian, Asian and African American, and so we have to use more than one binary variable. These binary variables are also called dummy variables. Okay, so we introduced two dummy variables in this case. The first one is 1 if the ith person is Asian, and 0 if the ith person is not Asian. The second dummy variable is 1 if the ith person is Caucasian, and 0 if the ith person is not Caucasian. Okay, now you could ask if we need a third dummy variable for African American, but as a matter of fact we don't need that. Why? Because when we use our two indicator variables, then we already are able to describe all the three cases. So let's look at the model. So now the model has the structure. You have beta 0, the intercept, and then we have a linear term in the first dummy variable, and the linear term in first dummy variable, linear term in the second dummy variable. And what does it happen? So if the ith person is Asian, we have beta 2 equal to 0, so the model becomes beta 0 plus beta 1 plus epsilon, so we have an intercept for Asian persons. If the ith person is Caucasian, we have beta 1 equal to 0, and so we have beta 0 plus beta 2 plus epsilon, and this is the intercept for the Caucasian persons. And finally, if the person is neither Asian or Caucasian, that is African American, in that case both the dummy variables are 0, so you are left with beta 0, and so this is the third model, and as you can see, in this case, the baseline is associated with African American. Okay, there is a rule that tells that the dummy variables are always less than the number of levels, and more precisely, if you have n levels, the number of dummy variables you need is n minus 1. So this is a simple rule you should keep you should keep in mind. In this case, we had 3 levels: African American, Caucasian, Asian, and the dummy variables were 3 minus 1 equal 2. Okay. All right. In the case when one, of course, it will always happen that one of the levels is associated with 0 values of the gamma variables. In this case, it is African American, and this, as I have already said, is known as the baseline. Let's look at the results for the ethnicity model. We now have 3 parameters, the intercept and 2 dummy variables. The intercept, this is the value. The standard error, as you can see, is less than 1/10 of the absolute value. The t-statistic is very large, the p-value is very small, so that's good. And let's look at ethnicity. Ethnicity, this is the parameter, and we see that the standard error, its value is larger than the absolute value of the coefficient. So we don't expect this to be a significant parameter. As a matter of fact, this is the value of the t-statistic, and the p-value is 0.77. So you get such a large or larger you get such a larger t-statistic in 77% of the cases, and therefore we are not able to reject the null assumption that this coefficient is actually equal to 0. A similar fate occurs to ethnicity, where the standard error again is larger than the absolute value of the coefficient. You can see the t-statistic, and this is the p-value. The threshold for the p-value usually is set at 0.05. So you can see here this is much less than that, and here it is quite larger than the threshold. So we do not have problems. Intercept is significant, but the other 2 parameters are not. Okay, that's for categorical variable. Now we have other 2 issues. We will discuss in some detail the first one, while the issue of nonlinearity will be treated later in the course. So let's introduce interactions. And we go back to our advertising data. You remember that we would like to discover what effect on sales has the expenditures in advertising on newspapers, radio, and TV. In particular, so far, we have assumed that the effect on sales of increasing expenditure in one of the 3 media is independent of the amount spent on the other media. So we have a linear model, and this is the model. Our prediction for the sales is the intercept plus a linear term on TV expenditure, advertising on TV, beta 2 times radio expenditure, and beta 3 times newspaper expenditure. So the idea is that when I increase one of these 3 expenditures, I should have some benefit on sales, but this benefit should be independent of what happens for the other 2 expenditures. So this is the meaning of the model. This is what the model tells us, but this could be too simple to describe what happens in reality, and let's consider the case when spending money on radio advertising actually increases the effectiveness also of TV advertising. This means that the slope term for TV is not a fixed slope term, but you can improve this slope, or you can change the slope by spending money in radio advertising. So in this situation, it may happen that if you have a fixed budget, let's say $100,000 that you can spend, and you spend half on radio and half on TV, this could increase your sales more than spending all the money on either TV or radio. When this happens, we say that there is an interaction, and in the marketing literature, this is known as a synergy effect. And now we are going to explore this issue of interaction and how we can model it. Okay, you can also try to see interaction from looking at the data, and in particular you could plot sales against TV and radio expenditure. And here what you are looking at is a three-dimensional scatter plot. So this is a scatter plot where the points represent data in a three-dimensional space. We have the two predictors, TV and radio, and we have the target variable, which is sales. And also here there is a plane which could be our linear model without interactions. And the interesting thing is that you can see then when you spend money on both TV and radio, that is these points here, these points tend to be higher than predicted by the model. So the plane provides you the model prediction. But in this case, the true sales are higher than predicted by the model. So the model underestimates. So it seems that there could be some interaction between TV and radio, because when you spend on both, you get more than the model without interaction is predicting that you should get. Okay, so let's go on and let's see how we can introduce interaction in our model. And the idea, okay, is to have some new dummy variable. Okay, so yes, not a dummy variable, a new parameter. So we have our model where we have the intercept, linear term on TV, linear term on TV, linear term on radio, and then we introduce another parameter that we call beta 3 that multiplies the product of radio and TV. In some sense, it's like creating a new predictor which is given by the product of radio and TV expenditure. Okay, so we had this predictor, TV, the second predictor, radio, and now we create a new predictor which is just the product of these two, and we associate a parameter to it. Now we can rewrite this model. This is quite easy. There are two ways to rewrite. The first one that we see here is beta 0, then we have beta 1 plus beta 3 times radio times TV, and then we have a linear term on radio. In this way, okay, I've highlighted the fact that the coefficients for TV is not a fixed one, not just beta 1, but the effect of TV expenditure on sales can be changed by radio expenditure, because this radio enters this part, this expression, and in particular it changes the slope by which TV affects the sales. Let's perform least squares estimation. So now we have 4 parameters. Beta 0 is the intercept, and then TV, radio, and the interaction parameter. And let's look at the coefficient, standard errors, and t-statistic. Again, here the intercept is highly significant. P-value is really, really small. The TV parameters is also very significant. Again, the p-value is much less than 0.05. As for radio, okay, again, this is has a very good significance. This statistic is 3.24. Recall that if you have a lot of data, then the t-statistic collapses to a Gaussian one, and the critical value is 1.96. So 3.24, if you have enough data, is actually quite a large value for the t-statistic, and this is recognized by the p-value, which is small. And finally, we have the interaction term. This is the coefficient. Standard error is even equal to 0 with this precision. The t-statistic is about as large as the one for the intercept, so this is very significant. So it seems that an interaction term was actually needed in our model. Okay, what's the interpretation? As I said, interaction are important. The p-value for the interaction term is very low, so there is a strong evidence for the assumption that there is this interaction. Okay, so we can reject the null assumption that beta 3 is equal to 0. And if we look at the R-squared indicator, we see that for the interaction model it is very high. It is 96.8% compared to 89.7% for the model without the interaction term. So we are quite happy with that. And in particular, it means that this is an easy computation, so we are looking at the increase of R squared, okay, compared to the unexplained variance. So we had an unexplained part that was 100 minus 89.7, because 89.7 was the R squared for the model without interaction, and we improve by this. This means that 69% of the variability that had remained unexplained with the additive model, the model without interaction, has now been explained by introducing the interaction term. So this is a very good progress, I would say. And we can also interpret the coefficient estimates, and in particular assume that we are increasing advertising on TV by $1,000. This will produce increased sales by this expression. So beta 1 hat plus beta 3 hat times radio times 1000, and these are the coefficient 19 and 1.9 times radio units. Okay, I've just made the computations, and so I can see the benefit of spending something on radio when I've decided that I'm going to spend $1,000 on TV advertising. On the other hand, I could also decide that I increase radio advertising by $1,000. In this case, the increase in sales will be this one. I can just compute the products beta hat 2 by 1000, beta hat 3 by 1000, and I get this expression that gives me the benefit of spending some money on TV, okay, spending some money on TV in terms of the effect of the expenditure of $1,000 on radio advertising. Okay. Okay, this is an important remark because we have learned that we don't like parameters whose p-value whose p-value is large, because the idea is that if the p-value is large, we are not able to reject the hypothesis that the parameter is equal to 0. So we will look at the p-values, and possibly the parameters whose p-values are large, above 0.05, will be discarded. Okay, but there is an exception. So when we are introducing interaction terms, it may happen that the interaction term is very significant, so it has a very small p-value, but the associated main effects, in this case, if the interaction term is TV, regards TV and radio, the associated main effects will be those relative to TV alone and radio alone, and it may happen that the associated main effects do not have a small p-value. So, in principle, you would discard the main effects in this case. So you would have a model where you have the interaction, for instance, radio and TV taken together, but you don't have TV or you don't have radio alone. As a matter of fact, this is something you should not do. Okay, so there is what's called a hierarchy principle that tells that if we include an interaction in a model, we should include also the main effects, even if the p-values are not significant. What's the reason? The reason is that if you don't introduce the main effects, then the interpretation of your results becomes very difficult, because the interaction has to take charge also of the main effects. So you cannot distinguish the real effect of the interaction, because in that coefficient you also have included the main effects. So this is an interesting exception that you should keep in mind. And this is just the explanation that so it's very difficult to interpret interaction without the main effects, because their meaning is changed in that they have to include also the main effects, because they are not in the model. So in some sense, the only way to account for them is through the interaction term. So don't do that. Don't discard the main effect if you are including the interaction terms. Okay. Next step is the use of interactions between qualitative and quantitative variables. Could seem difficult. As a matter of fact, it is not very difficult. Let's illustrate by the credit data set. And so we want to predict balance using income, okay, which is quantitative, and student, which is qualitative. So without interaction, we would have a model of this type. So balance would be beta 0, the intercept, plus beta 1 times income. So this is the coefficient for the quantitative variable income, plus beta 2 if the ith person is a student, and 0 if the ith person is not a student. Okay, we can rewrite this as intercept, as a linear term for income, plus two different intercepts. So if ith person is a student, the intercept becomes beta 0 plus beta 2. If the ith person is not a student, the intercept is beta 0. So actually you have two models. So you have a model for the students, a model for those that are not students, but the two models share the same slope for the income. So the only difference between the two models regards the intercept. So beta 0 is the intercept when person is not a student. Beta 0 plus beta 2 is the intercept if the person is a student. But the slope of the income term, of the linear term in income, remains the same for the two models that share this proportional dependence on income. Okay. Now, if we introduce interactions, the model will be written in this way. So we need a new parameter beta 3, that is the parameter for interaction between student and income, and we have beta 0 plus beta 1 times income, this is the main effect, and then we have beta 2, okay, which is the dummy variable for student, and then we have beta 3 times income. Beta 3 is the variable that accounts for the interaction between the binary variable student not student and income. So in this case, beta 3 will multiply income if we have a student, and instead, if we don't have a student, we will have 0. Now, let's rewrite the model in the two cases, okay? So, if we have a student, we have beta 0 plus beta 2, so this is the intercept for the student persons, plus beta 1 plus beta 3 times income. So, this time we have a specific intercept and a specific slope for the students. On the other hand, if the person is not a student, we just have beta 0, which is the intercept, and beta 1 times income, which is the slope. So let's go back. All right. Here we had a model with the same slope for students and not students and different intercepts. Now that we have the interaction term, we have a model with different intercepts for students and not students, and different slopes. This is the slope for student and not student. So we are more flexible. Okay, and this can be seen by looking at the models when we plot balance predicted by the model against income. So in the model without interaction, the difference between student red and non-student black is only in the intercept. So we have parallel lines. In the case when we have an interaction term, we get lines that are no more parallel because we have different intercept and also different slope. Okay, next issue could be dealing with nonlinear effects of predictors. So, so far we are considering linear models. Here we have another example. This is horsepower of a car, and here are the miles per gallon. So the idea is that if you have a lot of horsepower, then you are going to consume much gasoline, and therefore the miles per gallon are going to decrease. So these are the data, the circles. Then you can just estimate a linear model, that is the orange one, okay? And you can see that this is not bad, but as a matter of fact, it seems that there is something more than a linear dependence, so you could try with some polynomial model. In particular, here we have a degree 2 polynomial, that means a quadratic model, and this is the light blue, okay? You can see. And this is quite good. But you can also try with a higher order polynomial. This is a fifth order polynomial. But as a matter of fact, here you are at risk of overfitting. The model is quite weakly. Okay. And so the model, the plot suggests that this could be a good model. So a good model could be intercept plus linear term plus another coefficient that multiplies horsepower squared. And again, we are using a trick similar to the one used for interaction. So we are creating a new predictor. So we had horsepower as predictor. Now we take horsepower to the second power. So sorry for the joke, but horsepower squared. And by taking horsepower squared, we consider this as a further predictor, and so we can associate to it a parameter beta 2. And we can go and estimate this model just in the standard way, because this, as a matter of fact, is a linear model. It is like I have predictor 1 and predictor 2. So it is a linear model in predictor 1 and predictor 2. I have to estimate 3 parameters. These are the coefficients, the standard errors. Okay, here the t-statistic is huge, so very significant, but everything is okay also for the other two parameters. You can see t-statistic minus 15 and the t-statistic equal to 10, so they are really significant parameters. Okay, and so this is another issue, but we will discuss more about nonlinearities in the following lectures. What we did not cover in this specific lecture, we did not discuss outliers, but I have said something in our review of probability and statistics. We have already assumed that the variance of the error terms is constant, but in the real world it could actually be you could actually have a non-constant variance across the data, and this leads to weighted least squares estimation. So you are not giving the same weight to all residuals, but you will give heavier weights to residuals where the variance of the measurement is smaller. The issue of high leverage points, we have not discussed that, and also collinearity, and you can find this in the book in section 3.33. Okay, linear models can be generalized under different aspects, and in particular this is something that will be discussed later, so I just anticipate some topic that will be studied. So we will go beyond the linear model for what concern classification problems, introducing logistic regression support vector machines. We will also study nonlinearity by means of kernel smoothing, splines, generalized additive models, nearest neighbor methods. The issue of interactions will be addressed by tree-based methods, bagging, random forests, and boosting, that are also good at capturing nonlinearities. And finally, we will say something about regularized fitting, which is very popular these days, and in particular, we will introduce ridge regression and also the lasso. And this concludes our presentation of main topics on linear regression. Thanks.